In this short video, we're going to introduce the uh, hypothesis testing for the difference between two population means. And we're going to introduce both hypothesis testing and confidence intervals. We want to consider two populations where the population variances are known versus when the population variances are unknown. So why don't I just first start off with just giving you the formulas that we would use in those situations, and then we would move to a sample problem. All right. So the idea behind this analysis is that sometimes we want to compare two populations, and we are interested in whether or not the means are different from each other, whether or not the mean of one population is more than another. So if we had these two populations right here, one with mean mu1 and standard deviation sigma 1, and another one with mean mu2 and a standard deviation sigma 2. We are sometimes interested in whether or not the mean of 1 is greater than the mean of 2, HA, or whether or not the mean of 1 is less than the mean of 2, right, population 2. Or if there just simply is a difference between them, they're not equal. So those are the three research hypotheses that we could certainly consider. And the test statistic that we will use in each case will depend on whether or not we know the population variances or not. So let us start off with the case where we do know the population variance. All right. So if we know the population variances, so that is if sigma 1 squared and sigma 2 squared, that's the variances, or standard deviations, it don't matter, are known. So what is a test statistic, and then how do we find a confidence interval for the difference between the two means? So we're going to start off with a confidence interval for the difference between the two means. So a 1 minus alpha times 100% confidence interval for mu1 minus mu2. And remember that 1 minus alpha is the confidence coefficient. So if we're in a 99% confidence interval, 1 minus alpha is 0.99, which means alpha is 0.01. So it's given by the point estimate. Remember that for confidence intervals, they all have the form point estimate plus or minus a margin of error. But the margin of error is made up of a critical value and the standard error. So it should look something like this. X bar 1 minus x bar 2 would be the point estimate of mu1 minus mu2. The two things are consistent, right? And then plus or minus a margin of error. And that margin of error should have a critical value. Because we know the population standard deviations, then we would use Z, the normal distribution. In other words, the sampling distribution of x bar 1 minus x bar 2 would be a normal distribution. So we will use Z, and the standard error would be this, sigma x bar 1 minus x bar 2. But we could replace sigma x bar 1 minus x bar 2 with this formula. So it becomes x bar 1 minus x bar 2, that's our point estimate, plus or minus our critical value Z. And that, of course, is based on the confidence coefficient. And then the standard error for x bar 1 minus x bar 2 is sigma 1 squared over n1, sigma 2 squared over n2. All right? So that is the confidence interval for the difference between two population means when the variances are actually known. Excuse me. The test statistic now, if we're doing a hypothesis test, would simply be this. So now the test statistic it would be Z, of course, because we know the population variances. And if you recall the format of all of the test statistics, it was always the point estimate minus the population mean. So that gave us actually the sampling error, mu1 minus mu2. And it turns out that mu1 minus mu2 is the population mean of the difference between the two means. So if I know the two population means, then the difference between them is just to subtract them. And then, of course, if you recall, all of these test statistics have the format of the point estimate minus the population parameter divided by the standard error. And now the standard error in our case is sigma 1 squared over n1, sigma 2 squared over n2. Okay? Now, I'm just doing a quick review before I do the example, but really the details in terms of my explanation of all of this is actually in the video that I've already posted for you in the course outline. So that is when sigma 1 and sigma 2 are known. What happens when they are unknown? So if sigma 1 and sigma 2 are unknown, we have two possibilities. We could assume that the population variances are the same. So if they are unknown, we don't know what they are, we're going to make one or two assumptions. We could assume that sigma 1, the variances, sigma 1 squared is not equal to sigma 2 squared, right? The variances are not the same. Variances are not equal. Or we could assume that the two variances, sigma 1 squared is equal to sigma 2 squared, the variances are the same, is equal to just a constant value, right? That is, the variances are the same. So that's our assumption. This situation right here, we will not deal with that situation for our purposes. We're going to only consider this situation where the variances are the same. And in the case where the variances are the same, we will estimate sigma x bar 1 minus x bar 2 by this s x bar 1 minus x bar 2. In other words, sample, right? Sample estimates population parameter. So we will estimate with that. It turns out that what we will use for our standard error, so we will actually have sx bar 1 minus x bar 2. That will be given by the following formula. Sp squared times 1 over n1, 1 over n2. So that is what we will use as the standard error. And I'm going to explain to you very shortly why we have this. But let's give you a definition. This here, Sp squared, is referred to as the pooled sample variance. Okay, it's referred to as the pooled sample variance. And what it is that Sp squared is an estimate of sigma squared. All right? It's an estimate of that. Because remember we said sigma 1 squared is equal to sigma 2 squared is equal to sigma squared. In other words, they're the same. And so therefore we need to estimate the population variance. And we do that with a parameter, with a statistic called the pooled sample variance. So how then do we compute this pooled sample variance? The pooled sample variance, Sp squared, is given by n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by the degrees of freedom, which will be n1 plus n2 minus 2. So in this situation, we will have degrees of freedom n1 plus n2 minus 2, because we're going to need that, the degrees of freedom. Whenever we're dealing with a t-distribution, we need the degrees of freedom. All right? So we have SP squared. How we calculate that? We have the standard error that we're going to use. We have the degrees of freedom. And so here are the confidence intervals now and the test statistic. So a 1 minus alpha times 100% confidence interval for mu1 minus mu2 when the variances are unknown, is given by the following, which would be our sample estimate, x bar 1 minus x bar 2, that's our point estimate, plus or minus our t value now, t, and of course we use t alpha over 2 because we have to take the significance level and spread it between the two tails since it is a confidence interval, and then our degrees of freedom, df, which I gave you a little earlier, times the standard error, and the standard error we said is SP squared 1 over n1, 1 over n2, right? And then the test statistic now, t, is given by our point estimate, x bar 1 minus x bar 2, minus mu1 minus mu2, divided by the standard error, SP squared 1 over n1 plus 1 over n2. And that will give us our test statistic. So that's the information that we need for us to handle problems involving two population means. Okay? If we know the population variances, then we use what I discussed earlier. We use these values, this expression right here for the confidence interval and the test statistic. And then, of course, if it's unknown, then we use the concept of a pool sample variance, and then we will get the standard error as follows. Okay. Now, just to give you a quick sense, and I think I explained that in the video with the notes, just to give you a quick sense of what I mean when I say that we have to calculate this pool sample variance. Let's see why that is, and you don't need to actually write down notes in this section, but I just want you to understand why. So if we have a situation where, as we said, the variances are unknown, ideally it would be nice to just simply say that the test statistic, right? Let's just use the test statistic, is x bar 1 minus x bar 2, mu1 minus mu2, and then we would just simply use s1 squared over n1, s2 squared over n2. But remember that we made the assumption that the variances are the same. Population variances, that is. In other words, if I had the population variance, variances, which, and don't forget that the population variance is the same for both of them, I would just simply need to put sigma squared, right? Because remember that it's the same for both of them. If I put sigma 1 squared, sigma 2 squared, since they both are the same, I would replace it by sigma squared. Now, because I don't know them, I need a single value to estimate sigma squared. If I use the sample values that I have, it wouldn't make sense. S1 squared, S2 squared. If I did that, there's a pretty good chance that the sample variances S1 squared is not equal to S2 squared. But remember that we said sigma 1 squared is equal to sigma 2 squared is equal to sigma squared. In other words, they're the same. So how could I use two different values to estimate a single value? I cannot use that. So that means that I cannot use S1 squared and S2 squared in the standard error calculation because they would more than likely be different. But remember, the population variances are the same. So instead of S1 squared and S2 squared, what I need is a single value, and that single value is what we call SP squared, the pooled sample variance, right? SP squared, SP squared. Now that is the same value. And then we obtain SP squared by really combining the information from the two samples to create one. That's all we've done. So when we took I'll show you. So when we took the following, when we said SP squared was equal to N1 minus 1 times S1 squared, what we're doing is we're taking the sum of the squared deviations from sample 1, N2 minus 1, sum of the squared deviations from sample 2. We're combining them, hence we are pooling them. And then we're dividing by the degrees of freedom, N1 plus N2 minus 2, okay? And that's how we end up with a single estimate is by grouping the two, the information of the two samples. All right. It's kind of equivalent to when you have some bars where the different waiters make different levels of tips every night, but at the end they pull them all together and divide it equally amongst everybody. So in that case, that is an example of, and that is just an analog of what we're trying to do here. Is that we're taking information from the two samples, grouping it together, and then coming up with a single estimate. So now that we have all of that, let's actually go to a problem, all right? The problem I want us to consider is this very first problem right here, and it reads as follows. So let me just expand that a little bit. That we have the following. The USA Today reports that the average expenditure on Valentine's Day is $100.89. Do male and female consumers differ in the amounts they spend? The average expenditure in a sample of 40 meals, right? So we have N, that's a value of N right here, 40 meals, was 135.67, and then for 30 females was 68.64. Well, the standard deviation for males is assumed to be, so that's based on past surveys. So that kind of essentially means that we're taking that to mean the population standard deviation, right? Is 35 for males and 20 for females. And then we ask, what is the point estimate of the difference between the population mean expenditures for males and females? So of course, the point estimate is just the difference between the sample values, right? And then what is a 99% confidence interval? Or basically find the margin of error for 99% confidence interval and then put it all together in part C. So instead of going part A, part B, part C, I'll just find a 99% confidence interval for the difference between the mean expenditures, and then we will actually have all of those parts together. A, B, and C will just be combined into one. So let's do that. Okay, so I need to just make sure I got the information correct. And we have the following. So we knew that for men, I'm going to let 1 represent males and 2 represent females. So what information do we have? We have N1, we have 40 males, we have N2, 30 females. We know that the sample mean for males was 135, 135, and I believe, let me go back a little bit quickly, 135.67 and 68.64. 135.67 and 68.64 for females, X bar 2, all right? And then now we have population standard deviation. Sigma 1 was 35 for males, and sigma 2 20 for females. So given that information, we want a 99% confidence interval for mu1 minus mu2, the difference between males and females. So when we look at this particular problem, we see that since the variances are known, so therefore we would use this formula, x bar 1 minus x bar 2 plus or minus our critical value, z, times the standard error, which is sigma 1 squared over n1 plus sigma 2 squared over n2. So that's the formula that I gave you earlier when the variances are known. So all we got to do is substitute the values. 135.67 minus 68.64 plus or minus, and for a 99% confidence interval, I gave you guys that before, it is 2.58 or 2.575, which is what your book tends to use, and then we just plug in the values for the standard error. So it's 35 squared for men over 40 plus 20 squared for women over 30. As easy as that. And then what we will get is that our sample difference is 67.03 plus or minus, and if I'm not mistaken, I believe it is 2.575 times 6.63. That's what our standard error is, 6.63. When we compute that, that gives us 67.03 plus or minus 17.07. Okay? So now, what do we have now? When we add and subtract to get the interval, so we have mu1 minus mu2 lies somewhere between, and when we do the addition and then subtraction, we should get 49.96, right, and to 84.10. So, and that's in dollars. So we are 99% confident that the difference between the means lie between $49.96 and $84.10. So from that information, you can infer that men on average spend more money because any value in that interval is positive. The minimum is like $49 and the maximum is 84. So we are 99% confident it's between 49 and 84. So any value in that interval is suggesting that mu1 is greater than mu2, which basically means that men are spending more than women for Valentine's Day. That's because men have to buy more chocolates and roses and all of these fancy things, all right? So we could just put a statement that says, we are 99% confident men spend on average between 49.96 and $84.10 more on Valentine's Day compared to women. All right? So that's our conclusion based on that, because any value in that interval is positive. It's a positive difference. And if it's a positive difference, it suggests that mu1 is larger than mu2. Okay, so that's our conclusion with that. One of the things to note is that as long as that interval does not contain a 0, if the interval contains a 0, then it's possible that it could be the same, right? Because 0 difference means that mu1 is equal to mu2. A negative difference means that mu2 is larger than mu1. And then a positive difference means mu1 is larger than mu2. So if your interval straddles the 0, then you don't have evidence which one is greater. Because remember, it doesn't matter even if it was like from negative $2 to $84. You can't say, oh, it's more on the positive side. You can't say that. All we're saying with this interval is that the difference is somewhere in that range. We don't know exactly what it is. It's just in that range. And so therefore, if that range is completely positive, then mu1 is greater than mu2. If it's completely negative, mu1 is less than mu2. But if it goes between the two, then we're not sure. We could kind of illustrate this in this fashion, where let's say that's the difference curve. So on that side, this is the positive, negative, and this is 0. So if I have an interval here that goes from here to here, then, and remember we're looking at mu1 minus mu2. If the interval is on the right side, then it means mu1 is greater than mu2, right? If we have an interval on the left side here, then mu1 is less than mu2. But if you have an interval that goes across the two of them, then we're not sure. All right? So that means that the interval goes across the 0 mark. And at the 0 mark, remember that the means are the same. So here is mu1 is greater than mu2. Here, mu1 is less than mu2. And then at this point, mu1 is equal to mu2. So when your interval goes across the 0, all three of those are possible. But when it's strictly on one side, only one thing is possible. Either mu1 is less than mu2 or mu1 is greater than mu2. All right? So keep that in mind. Make the notes that will help you with that. So that was the confidence interval question with that. We're going to continue now with the hypothesis test. And what we're going to test is there a difference between men and women in terms of their expenditures? So I'm going to actually take this very same problem and repeat it, but as a hypothesis testing problem, okay? So I'm going to test, is there sufficient evidence of a difference between the mean expenditures of men and women? So 1, we would have a hypothesis. So HO. So we'll say there is no difference between the mean expenditures versus there is a difference between the mean expenditures. So no difference between the mean expenditures all right, versus there is a difference between the mean expenditures. And then writing that in terms of symbols, sorry, HO and HA. If there's no difference between the means, then we're saying mu1 minus mu2 would be 0. Because if they're the same value, when you subtract them from each other, we are essentially going to find a difference, which is 0. I mean, a no difference, which is 0. But mu1 minus mu2, sorry. 1 minus mu2 is not equal to 0. That means that there's a difference between them. We're not sure this. We're not actually making a claim about which one is larger. All we're going to claim right now is that there is a difference between them. All right. So mu1 minus mu2 is not 0 versus mu1 minus mu2 is equal to 0. So that's our sorry, I went too far. Let's do step 2. Let's see if we could make use of the space over here. Step 2. So step 2, we want to test statistic. So it would just be, since we're actually going to start off with the variances known. So step 2, the test statistic would be x bar 1 minus x bar 2, that's our point estimate, minus mu1 minus mu2, our population parameter, over the standard error. And what's the standard error in this case when the variances are known? Is sigma 1 squared over n1, sigma 2 squared over n2. That's step 2. Step 3, our decision rule. So if we look at the decision rule, it's a two-tailed test because we have not equal to, so therefore we could be looking for evidence in the upper tail or the lower tail. So it's a two-tailed test. So our critical values are Z criticals. Because we want a 99% confidence interval, alpha, which is our significance level, is 1%. Sorry, not a 99% confidence interval, a 1% significance level. So alpha is 0.01. We're going to make it equivalent to the confidence interval problem. So that means that this is alpha over 2 in this corner, 0.005, alpha over 2 in this corner, 0.005. We have to split it between the two, and that makes our z value 2.575. That's our critical value, negative 2.575. So reject the null hypothesis if we're in this region, and then also down here. So if our z value, and what I'll do is I'll say if the absolute value of z, just in case it could be a negative value, is greater than or equal to 2.575, we will reject HO. We'll reject the null hypothesis. Okay? The p-value approach is if the p-value is less than alpha, or if the p-value is less than alpha. Reject HO. Step 4, our analysis. So in that case, let's find our z value. It would be x bar 1 minus x bar 2. We've already calculated what that is, which it turns out to be 67.03. We did that in the last problem where we subtracted the two sample means, so we could just put 67.03. From the null hypothesis, the difference is 0. Mu1 minus mu2 is 0. And then we just simply put our values in the standard error, which we've already calculated before in the last problem when we did the confidence interval, to be 6.63. But I'll just write it out here for you, which is the 35 squared over 40 plus the 20 squared over 30. When you do the calculations on that, you will end up getting a 10.125. And as you can see, this is much larger than 2.575. All right? Now, what is our p-value? We always go ahead and find the p-value. We don't want to just get stuck with only the z value. So our p-value, in this case, p-value, because it's a two-tailed test, means that we have to multiply twice the probability of z greater than or equal to 10.125 or 10.13. Okay, twice that. Now in our table, we do not have we certainly do not have a 10.125. What we know is that at 3.09, the area left in the tail is 0.001. So this portion right here, this portion is less than 0.001. So if I multiply less than 0.001 by 2, I will get less than 0.002. So our p-value is less than, I shouldn't put equal, I should just say, put in equality one time, is less than 0.002. All right? And as you can see, that is also less than alpha, which is 0.01. So we'll reject the null hypothesis anyway. So last but not least, our decision conclusion. Okay, decision conclusion. So step 5, decision conclusion. So since, if we're doing the critical value approach, 10.125 is greater than, not just greater, but much greater than 2.575, we will reject the null hypothesis. If we were applying the p-value rule, we would also reject the null hypothesis because the p-value we know is less than 0.002. Our alpha value is 0.01, so therefore it is less than 0.01. And we would reject the null hypothesis. So we reject the null hypothesis. What do we conclude? We conclude there is sufficient evidence or significant evidence, sorry, strong evidence. There is strong evidence of a difference between, okay, there's strong evidence of a difference between the population means, between the mean expenditures of men and women for Valentine's. All right, so that's it. That's our conclusion. What's our actual p-value? Not p-value, but our what type of error might we commit? The type of error, possibility of type 1 error. Type 1 error, since we rejected the null hypothesis. And what's the probability of type 1 error? P type 1 error is always the p-value, right? Which we know is less than 0.002. So the risk that we're taking in committing type 1 error is really less than 0.002. So it's small. It's much smaller than the 1% that we set for ourselves, and that's why we're willing to reject the null hypothesis. Okay, so that actually concludes doing both a confidence interval and a hypothesis test, when the variances are known. So I'm going to pause the video here and then continue with a part 2 where I will repeat the problem, but now I will actually do it with and pretend that the variances are unknown, so that those variances that we have are sample variances. Okay, so I'm going to actually pause right here. Excellent.